So in this example, we're given that a granular material exerts a distributed load on the beam from point A to point B, and we're asked to determine where is the magnitude of the resultant force and where is the location of the resultant force along the beam from point A to point B. So for this type of problem, we don't have a obvious distributed load or an obvious shape for our distributed load, and we were not given W of x in this case. So what we can do is we can treat this problem as being the combination of two simpler problems. So we could treat this as being this problem, which we have a 50 pounds per foot distributed load from point A to point B, plus the addition of a triangular distributed load from point A to point B, where its maximum value would be at 50 pounds per foot, and its smallest value would be at 0 pounds per foot. Right? So for both of these simple cases, it should be really easy to calculate what is the resultant force, so I'm going to call this FR1 from the distributed load, and where that concentrated force is being located. So we can do that for both of our cases here. Right? And then at the end, once we have FR1 and FR2, what we can do is we can combine them to get our total resultant force, FR, and our total centroid, X of C. All right? So that's what we're going to do in this problem. So we're going to start with each of these simpler cases. This case 1 and case 2, and then we're going to combine them. We combine case 1 and case 2 to get our original case on the left-hand side here. Okay, so let's start with case 1. So what we need to do is we need to find FR1. FR1 is going to be equal to the area under the distributed load curve. All right, so in this case, we have a rectangular distributed load, so it's going to be equal to 50 pounds per foot times the total length of our beam from point A to B. So that's going to be equal to 9 feet. All right, so 400, that would be equal to 450 pounds. Okay, and then XC of 1, or the centroid of that area for a rectangle, is just going to be equal to the length over 2. So it's going to be equal to 9 feet divided by 2, or 4.5 feet. Okay? If you're unsure of what would be the area for your shape or what would be the centroid of your shape, you can look at this following table here. All right, and it'll tell you for a square, for example, it would tell you the area of the shape here, okay, and it would tell you that the centroid is located at half of the base of the rectangle. Okay, so we can do the same thing. Go back here. We can do the same thing for our case 2. Okay, where we would say FR2 would be equal to the area under the curve. So in this case, the area under the curve would be equal to 1/2 times 50 pounds per foot times 9 feet. So this would be equal to 225 pounds. All right, and then for FC2, that would be located at the centroid of our triangle. So the centroid of our triangle for a right triangle is equal to 1/3 times the base. So it's going to be equal to 1/3 times 9 feet. All right, and that's going to be equal to 3 feet. Okay. All right. So to combine the two cases, all right, to get the total resultant force, that's really simple. That's just equal to the sum of all of our forces. So in this case, it'd just be equal to FR1 plus FR2. All right, so for FR1 plus FR2, that's just going to be equal to 450 plus 225, which is going to equal to 675 pounds. All right, and then to figure out X sub C, right, X sub C needs to create an equivalent moment about point A. So what we're going to do is we're going to sum all the moments caused by our force R1 and force R2 about point A, or the leftmost side of our beam, and we're going to divide that by X sub C, all right, or divide it by FR, sorry, to get our moment arm. All right, so if we do the moment due to our case 1, that's going to be equal to FR1 times XC1 plus FR2 times XC2 divided by our total resultant force. So we would get 675 pounds in the denominator, and our numerator would be equal to 450 pounds times 4.5 feet plus 225 pounds times 3 feet. All right, so this ends up being equal to 3 feet plus 1 foot, which is just equal to 4 feet for sub C. All right. So to wrap up what we did here is we broke our distributed load into two simple shapes, and then for each of the simple shapes, we determined what was the concentrated force and the concentrated or the location of where that concentrated force was. And once we had these two concentrated forces and moments, we then summed the two forces together, FR1 plus FR2, to get our total resultant force. And then to figure out where X of C was, we calculated the total moment about point A of our beam, and we divided by our total resultant force to get our X sub C. And that concludes this problem on finding the location and magnitude of the equivalent resultant force due to a distributed load.